Hey guys, this is Professor Janacek, and I want to go over a couple of examples of using Euler's method to approximate the numerical solutions of a differential equation. Just as a reminder, with Euler's method, we're going to be using the fact that y sub n plus 1 is equal to y sub n plus h, where h is our step, times f sub n, which is our derivative function evaluated at the n values. Okay, so let's see. Example number 1. We have y prime plus 2y is equal to 2 minus e to the negative 4t with the initial conditions y of 0 is equal to 1. Our step h is equal to 1/10, and we want to find approximate solutions at t equal to 1/10 and t equal to 2/10. I will want you to notice that this is a first order linear and it actually is solvable. So rather than finding approximate solutions, we could find exact solutions. Right, but how do we begin? Well, let me first start by rewriting that equation and isolating that derivative. So we've got y prime is equal to 2 minus e raised to the negative 4t minus 2y. This is the function f, so let's just rename this. This is f of, notice this is a function of both t and y. And so that's equal to 2 minus e to the negative 4t minus 2y. And we also have those initial conditions, t naught is equal to 0, and y naught is equal to 1. So let's begin by figuring out what is f naught. Well, remember f naught, that is that function f evaluated at t naught and y naught, so 0 and 1. So that would give us 2 minus e to the negative 4t minus 2. Oh, wait, what am I doing? Let's actually evaluate this. That is 2 minus e raised to the negative 4 times 0 minus 2 times 1. Let's see, what does that give us? E to the 0. Oh, that's going to be, what, just a negative 1, I believe. All right, there we go. So now I'm going to use my little formula for Euler's method to determine what is y1. Well, y1 would be y naught plus h times f naught. Well, in this case, y naught is 1 plus h is 1/10 times f naught we just found is negative 1. That gives us, let's see, what do we have? 9/10 there. Thus, at t equal to, this is our first step, so we started at 0, right? My initial t value was 0, and I went one step above that, so 0 plus 1/10, so we're now at the t value of 1/10. We have y1 is equal to 9/10, and this is the approximate solution. All right, so that gives us the first one, t at t is equal to 1/10, and we also want to find a solution at 2/10. Well, we'll go ahead and use this solution to find f1. Remember, f1 is f evaluated at t1 and y1, so that is f of 1/10, 9/10. Using, again, t1, oh, maybe I should put that there, t1 and y1. Putting that into our function, again, just going to evaluate that to this function here. We get 2 minus e raised to the negative 4 times 1/10 minus 2 times 9/10. Now take a moment, do this computation. You should get the approximate value negative 47, actually I'll go a little further, 4,703 10,000. So that allows us to find y2. Remember, y2 is y1 plus h times f1. y1 is 9/10 plus h, which is 1/10, times that f1 value, which is 4,703 10,000. Again, we can get a decimal approximation for that. And using a calculator, let's see, we get 8,000. Actually, I guess we could just round it to 853 thousandths. Thus, at our T2 value, which is now 2/10. Again, remember T1 is 1/10. My step is 1/10. Put those together gets me to T2, which is now 2/10. The y2 value that we've approximated is 853 thousandths. This is the approximate solution. Okay, not so bad. Let's try another one. Looking here at example 2, we have y prime is equal to 3 minus 2t minus 5/10 with the initial condition y of 0 is equal to 1. Here our step h is equal to 2/10, and we want to find the solution at t equal to 2/10 and t equal to 4/10. So the first thing we'll do, I've already isolated the y prime, so I don't have to do that like we did in the previous one, but I will go ahead and name our function just so I can reference f of ty is that derivative 3 minus 2t minus 5/10. You know what, just to make this a little more interesting, let's put a y on there so we have a y in this equation. There we go. Put a y in there. All right, and we also have that t naught is equal to 0 and y naught is equal to 1. So let's go ahead and use this to find our initial function value. F naught, which is simply f evaluated at t naught and y naught. So f of 0, 1, that is 3 minus 2 times 0 minus 5/10 times 1. Oh, let's see, just be clear on this. Let me rewrite that so you can read it. And what does that give us? 3 minus 5/10, that's 2 and 5/10. So there's f naught, and now we're ready to figure out the y1 solution. y1 is, remember, y naught plus h times f naught. So in this case, y naught is 1 plus h, which is 2/10, times f naught, which is 2 and 5/10. And what does that give us? 1 plus, 1 and 5/10. Thus, at, what is our t value? Well, let's see. Notice our t naught is 0, our step is 2/10, 0 plus 2/10, So our t1 value is 2/10. Perfect. That was the first value that we were solving for. So at t1 equal to 2/10, we have y1 is equal to 1 5/10. This is the approximate solution. All right, so that takes care of the first one. How about at t equal to 4/10? Let's see. Let's continue on now and just use that first value. Let's find f1. Remember, f1 is the function f. Remember, here's our function f, evaluated at t1 and y1. So that's going to give us f1. So f evaluated at 2/10 and 1 5/10. So what does that give us? 3 minus 2 times 2/10 minus 5/10 times 1 5/10. Oh, there's a little more going on here. Let's see, what is that? I think that should be 1 85/100. Okay, so now we can figure out what y2 is. y2, again, is going to be y1 plus h times f1. Well, y1, we said, is 1 5/10 plus h, which is 2/10, times f1, which we just found to be 1 85/100. Let's see this one. This one should end up giving us 1 87/100. Thus, at t2, what is t2 now? Let's see. t1 is 2/10. My step is also 2/10. Put those together, and that gives us a t2 value of 4/10. Again, this is perfect because that's what we were looking for. And at t equal to 4/10, the y value, which we called y2, is 1 87/100. This is the approximate solution. And there you go, Euler's method. Fun, fun. Enjoy.